The quiz on 21 is next Tuesday. By the way, I've been asked to let you know that if you're dropping the course, you have till through Friday. At some point on Friday. All right, still the sound. If I have a very still pond, and I throw a rock into it, right there, what's gonna happen? So I got ripples expanding now, so let this be the moment that the rock hits the pond. And then a moment later, the ripple that formed will have gotten bigger. And so it just starts spreading out. So these are moments in time. This is whatever the first time is, and this is the time where I throw a second rock in and I hit the exact same spot because I'm that good. And so I get a second ripple. So that first one, and then some equal amount of time later, that first one will now be twice the diameter it was before, and then the second ripple will be there. And then I hit a third rock in the exact same spot, and I create another ripple. So what you see are these concentric rings. If you're a bug on the water, let that be a bug on the water.
Looks like a reindeer.
It's the famous reindeer bug, water bug. Then you're going to get hit by the first ripple, then the second ripple, the third ripple. The time in between it will be the same. From that, the bug can then calculate, just looking at the stopwatch, go, okay, I know what the period of the wave is. And it should match exactly the same period. Time it takes for me to throw a rock in and then put a second rock in the exact same spot. Remember that period of frequency, or inverses of each other. So the frequency with which I throw rocks into the pond will be the same frequency that the bug senses. Scenario number 2, I throw a rock into the still pond, and it creates a ripple that gets bigger, and then bigger, all centered around where that first rock hit. This time when I throw the second rock, I don't throw it in the exact same spot. I throw it off to the right. So this is sort of the spot where the first rock hit. Then I throw a second rock a little bit off to the right. And so the ripple created from this one is centered in a different spot. And then I throw a third rock. However far off I was to the right, I go that much farther off again. And so what I'm going to end up with is another set of ripples that's closer to one side than the other. I still am throwing the rocks into the pond at the exact same frequency as I did before. I just not throwing it in the exact same spot. But if you're the bug on the water, apparently he's gotten bigger. What is the frequency he's going to sense?
Where is he on the water?
He's somewhere where he's going to get hit by the ripples.
Well, I know, but depending on where the bug is, like if he's off to the left.
No, he's exactly where I brought him. He's on the right.
Okay.
He gonna hear harmonics of that frequency.
I'm just sensing ripples right now.
Okay.
It's gonna be like
Third.
if it's closer to him, it's gonna feel like a stronger frequency.
Not because he's closer to it.
Period. Shorter.
Yeah, he's going to get hit by the waves more frequently. Now, it should be a larger amplitude because he is closer to where the second and third rock are. The first rock is still the same distance away. But he's going to get hit more frequently, or the period is smaller. Now, if he's been over here, as John was sort of heading towards,
Would be slow.
be careful about the wording there.
That's slower. You hit with a slower frequency.
Yeah.
Less frequently.
Okay, less frequently, or in terms of period? Bigger period. All right. Obviously, if this is sound, you would hear a higher pitch or hear a lower pitch. But the frequency with which it is produced is not the same as the frequency with which it's perceived. This is known, as I'm figuring most of you know, as the Doppler effect.
Radar?
Yeah. Now, I don't know how Doppler radar actually works, whether they just took the name or whether it actually has some other aspect to it, but.
All I remember about the Doppler effect is that we did an experiment outside of class near the road, and we would explain that the cars moving by would have a lower frequency when they passed us than if they weren't coming toward us.
Yep. So that's a, yeah, because as the source and the receiver are getting closer to each other, you get the higher pitch. If it's going away, if they're getting separated, it's a lower pitch. So that's why you get that sound as it goes by. Or even if you're looking at electric cars, that there should be a change in sound, though less noticeable. Now think about the first situation where I'm throwing the rock in the exact same spot. I got ripples going out, and so for the bug standing still on the side, he measures the same period I do. But suppose instead the bug is actually moving that way. And he's measuring how long it takes to get from one wave to the next. What would he say about the period?
A little shorter. Sure.
So, which means a greater frequency. He's hitting the waves more frequently. So Doppler effect happens as long as the source and receiver are getting closer to each other, whichever one is, it doesn't have to be just the source moving or just the receiver moving, and both of them are moving towards each other, we're going to get a higher frequency. So let's go through the fun of deriving it. Let's derive the equation. And so I have some object here that's emitting sound. So I'm going to use S for source, and then R for receiver. So the source produces a sound, and that sound wave was going to travel a certain distance. So I'm trying to figure out how to color code this. I'm going to color code it. So I'll use black for sound, and then I'll use a different color for his moving. So at some point later in time, the wave has moved this distance right here, and I'm just going to make it a flat wave. So it has traveled whatever the speed of sound is. I guess I'm already using S for source. I'm going to change that. I'm going to use E for emitter. And I'm going to use S for sound. So the distance that the first wave has traveled is the speed of sound times the period of the emitter. Because after this wave has gotten to there, the emitter has moved and it's going to emit a second sound. And so this is how far the emitter has moved, and it is going to be the speed of the emitter times the period from the emitter's point of view. Meanwhile, the receiver is heading towards him. The receiver is going to move, in that first time, is going to move some speed, V sub R, times whatever the period is from the emitter. Yeah, somehow I think I want to change this around a little bit, but. Well, I need to figure out how long it takes for the receiver, when the receiver passes this wave, how long does it take for the receiver hits the next wave? So the receiver's gonna pass this wave right here. It's gonna hit the second wave, well, it's gonna meet it at some point, because it got this first wave, it hits the first wave, the second wave's coming towards them. So, in the time it takes for the receiver to hit the wave, the receiver has moved, however fast it's going, times the time that the receiver is hitting the waves. And this first wave is gonna move whatever the speed of that sound is times however much time that is. And that is a incredibly sloppy diagram. Give me a moment here, just want to make sure. I usually just do one at a time, so I'm going bold here. I'm going to redraw this. I need it bigger. So the emitter gives off sound, and that first sound wave is, we'll just say here, by the time the second wave is being sent. So this distance here is the speed of sound times the amount of time it takes for the emitter to give up the sound. It's going to give up the next sound. Well, this guy is moving at some speed, v sub e. And so it's going to travel v sub e times t sub e, so just basically speed times time. That's how far he will travel by the time when he gets off the second wave. So this distance right here is, well, vs t sub e minus ve t sub e. Just that distance minus that distance. The receiver is at this point right here, so we're gonna make that the receiver. The receiver is heading in that direction. At some speed v sub r. And he is gonna get the second wave at some point in between here, because they're coming towards each other. So we'll just say at that point right there, he has traveled a distance of however fast he's traveling times the period from his point of view. It's the time it takes to get from one wave to the next wave. In that time, the second wave here has traveled this distance, which is how fast, that wave is traveling times the period that the receiver is getting. So we have VSTR plus VRTR is equal to VSTE minus VETE. So the distance from here to here, we look at it two different ways. We look at it from the point of view of the time from the emitter's point of view, and then from the point of view of the time of the source, of the receiver. Let's factor out what we can. So we have TR, here we go, all right. VS plus VR, just factoring, is equal to, over here I have TE, VS minus VE. So I can express this relationship in terms of the period. So the period that the receiver senses is just going to be the period from the emitter's point of view times, well, a fraction of Vs, the speed of sound minus the speed of the emitter, divided by the speed of sound plus the speed of the receiver. We can do it in terms of frequency, because frequency and period are reciprocals of each other, so this is 1 over the frequency of the receiver is equal to 1 over the frequency of the emitter times this. Or more commonly written, the frequency that the receiver is picking up is equal to the frequency that the emitter gives off times, we're doing the reciprocal of everything, so the speed of sound plus the speed of the receiver divided by speed of sound minus speed of the emitter. This is the more common form of the Doppler effect. So just do some number plugging, plug and chug here. So let's just say the speed of sound is 340 meters per second. The emitter, so somebody on the horn, on the car horn, let's just say 440 hertz, traveling this way. That is horrible notation. That's the frequency that's being emitted. The speed of the emitter, we'll make it 20 meters per second. Meanwhile, somebody's running straight at it. Speed of the receiver, whoever's carrying the sound, is, say, 15 meters per second. So the question is, what's the frequency that the receiver is going to hear? Well, it becomes a straight plug and chug. The frequency that is going to be heard by the receiver over here is 440 times 340 plus 15 divided by 340 minus 20. And you end up with something if someone's going to share. .440 times the fraction, 355 over 320. Pardon?
You said times that, right?
Yeah, times the fraction.
Okay.
488.125.
Units?
Oh, wait, hertz.
Yeah. So you're definitely going to hear a higher frequency there. And I think anyone who's stood by the side of the road has experienced this. Now, I did this for the situation where they're coming towards each other. If they're not coming towards each other, if one of them is going away or both of them are going away from each other, then the equation has to change. And it's not a dramatic change, but if one of them is trying to get away from the other one, that's going to reduce the frequency that's being heard. And so we need to accommodate that. So typically, they take our equation over there. That's Vs plus minus Vr over Vs minus plus Ve. Just to accommodate the fact that it could be going up or down. And if you get confused, think about it. All right, so if it's going away, it wants to reduce it. So if it's the receiver going away, I want to reduce this fraction, so I'm going to subtract. If it's the emitter going away, I want to make the denominator bigger, so I'm going to add. So for example, let's do a pursue and chase scenario here. We've got a police car emitting, what the heck, it's a make-believe problem. Let's say they're hitting 440 hertz again, police car. bad guy. Bad guy's moving away, so let's say the police car is going at 30 meters per second. So medium speed chase. Bad guy going at 30 meters per second. What will the bad guy hear? Well, the frequency that will be received will be 440 hertz. My fraction, the first part of the fraction is the speed of sound, which we'll still say is 340. So which one's plus, which one's minus, or are they both plus, or are they both minus?
The top one's minus, the bottom one's plus.
All right, big guy's, the bad guy is trying to get away, so that's gonna try to reduce it. He's trying to approach. So you said the bottom one was what?
Plus.
Except the police car is trying to get closer to him. The police car is trying to increase the frequency. In the scenario when the emitter was getting closer to it, it was minus.
Oh, okay.
So 340 minus 30, 340 minus 30. So what will the bad guy hear?
440.
440.
It won't change. If they're traveling the same speed. All right, questions up to here?
So, it's gonna be minus over minus if they're going, like, following each other.
If the emitter is following the receiver, if it's the receiver is chasing the emitter, so somehow it gets turned around and the police car's running away and the bad guy's following, but the police car's the one still on the horn, then it would be plus plus.
Okay.
So if the emitter is the one that's following, then it's minus minus.
Right.
Okay.
And then if the, emitter is staying still and the receiver